I've been promising for some time to make some more tutorial videos for this DX27. And you've got a number of great videos online exploring different aspects of the programming and how to set up the voices and so forth. But I've never really done a complete example. So I'm going to refer you to several other videos along the way. For example, to be familiar with all the settings for the envelope generator, I did a specific video on the settings of that, and I did some other videos about, I remember doing the compare and edit function. So we're going to just go through the procedure fairly fast just to get you making some new sounds. The first thing you want to do as you're exploring and inventing sounds from scratch would be to press the function button. Here it is, compare and function. Then right now it's saying init voice, but if it's not saying init voice, you can come over here and you can press the init voice button, which is button 7. Notice it says init voice there, and you will see init voice. So you press the yes button over here, and then it asks, are you sure? And you press the yes button again, and you see that screen. Now if you touch the keyboard at this point in time, you're going to hear just a plain sine wave, which is not particularly interesting because only the carrier is active. So it's normally assumed, based on what is recommended with FM modulation, that if you want to create organ voices, you're going to use a parallel stack like what we have here in algorithm 8. In other words, all the operators are going to be at the carrier level, and you won't worry with any modulators because the only modulation you'll be doing, or likely doing, is pitch modulation for vibrato. But it's very interesting and informative that we can actually get a good organ sound with a stack. There we're going to pick stack, the second stack, where the operators are pretty much stacked one on top of another, with the higher ones of course being modulators. So let's select algorithm 2 and see what we can do with that. So we press the algorithm button, and that moves us to the algorithm screen, and we just move the data lever. The data lever is what changes all these numbers. Just move it to algorithm 2. And once you move it with the lever to algorithm 2, it's pretty much going to hold that. But you're not really going to hear any difference in the sound because the operators are still sine waves, and only the carrier, or the 1, in this case operator 1, which is at the very bottom of the stack, is going to be sounding. How do we know this? I mean, well, all you have to do is to push the output level button. See here, the output level button, operator level. And when we come over here, we see out 90, up 1. So we're getting a 90, which is, it goes from, let's see, it goes from 99, 0 to 99. And that's basically just a volume on each operator. And operator 1 is set to 90 by default when we initialize our voices. So let's leave it at 90, shall we? Just put it at 90. There we go. Now when we go to operator 2, how do we do that? Well, we press this operator select button here, and that will change and cycle through them. So notice operator 2 is set to 0, operator 3 is set to 0, operator 4 is set to 0. So the only operator that's active is operator 1. And since operator 1 is a carrier on all the algorithms, that's why our change to algorithm 2 made absolutely no difference to the sound. So having decided we want to make an organ and type of voice with our algorithm 2, the natural step would be now to raise the various levels on all the other operators that are there, just to see what it does. Okay, so how do we do that? Well, once again, we press our operator select button over here, and we simply raise our data lever. Here's our data lever, but we're not going to make them all 90. We don't want to have them all. It's only natural the carrier will have the highest of the lot. So let's go for 53, 64, and 68, not because of any particular reason. Let's just see, 53. Press operator select, go to 64, and go to 68. Now feel free to experiment. Half of the thing that we're doing here is experimenting, and you learn by experimenting. Okay, let's get it to, actually 68 or 69 is not really going to make a big difference. As a matter of fact, you're going to realize that all the changes that you make are going to be extremely subtle. And in these ones where we can go from 0 to 99, just a single digit is unlikely to cause a major difference in the sound. In some cases, you may not even be able to hear the difference. So it's important that you don't get hung up on these numbers, okay? But when we play the keyboard, it's not a sine wave anymore, because you're hearing now a little more body to it, but at the same point in time, it's still quite far away from an organ. So what do you think could be the reason for that? Well, the next most important thing, in addition to operator level, is the ratio of the various operators. You see where it says here, oscillator frequency ratio. So you press number 13, and over here we see F equals 1.00 on operator 4. So once again, we cycle through the operators, and we discover that they're all set to 1. That's the reason why we're not getting that nice rich lot of frequencies, lot of harmonics that you would normally associate with the timbre of an organ voice. So this is the first thing that we have to fix. We have to change these ratios. Now, we're always going to leave the operator that selects the keyboard pitch, which is the carrier, at 1. Okay? 1 is going to determine the carrier pitch, the actual pitch of the keys you play on the keyboard, because 1 is the carrier for all of these stacks. So for the first 4, which are stacks, we call them stacks because the operators are stacked one after the other. So for algorithm 1 to 4, we've only got 1 operator as a carrier, and it's pretty important, if you want to have the key pitch correct, that you leave that one set to 1. But we certainly can play around with the other operators, and we're going to do that now. Let's change it to operator 2, and let's make operator 2 a whole number or integer. As long as you use integers on your operator ratios, you're going to get pretty nice harmonics, right? You're good. If you use a strange number, we'll show you that with decimal places, then you're going to get a sort of metallic or sound which is more like noise rather than a musical sound. So and if we want to play musical sounds, we need to keep our operators as even numbers. So we've made operator 2 3. Does that affect our sound much? Let's have a little. Right, now you can hear that we have some more frequencies, different frequencies in there. It's getting a little more thick. So let's try making operator 3. Let's move that away from 1 and let's just put that to 2 because we had 1 and 3. So let's just put that to 2. Put that to 2. They're sometimes a little tedious to get the exact value you want. There we go. Operator 3 is set to 2. Now we're going to hear that. Let's now go and it's getting more like reedy or brassy, should we say. Let's now go and look at operator 4, and let's make operator 4 ratio 4. Now the higher the ratio that we go, the higher the pitch is going to be. It goes up an octave for each one. So in other words, if we put 2, that'll be an octave higher, 3 an octave higher, 4 is an octave higher. So we would expect that by adding 4, we're going to get a very, very high-pitched sound in there. But remember, operator 4 is a long way above the carrier, and it's only going to affect the timbre rather than the actual frequency. So it's not going to change our keyboard pitch, but it's going to add some harmonics. See what a difference that made? Now it's sounding like an organ. So what's missing? What would be the next best and fastest way to get our organy type of sound? Remember, I am defying the odds. Most of the books that tell you about FM programming say if you want to make an organ, you don't use stacks. But the thing is, you can do it with stacks because stacks adds harmonics, and harmonics is what you need for that organy type of sound. So the next thing we're going to do is add what organs most love, vibrato. So if we press here, we see that it's set to a triangle wave, which is quite okay. Alright, so we've got 35 as our rate or speed. And the next thing that we do to get vibrato is we want to increase the amount of PMD. That's pulse modulation, pitch modulation depth. That's what it is. Pitch modulation depth. So we come here now with our data wheel and we move our pitch modulation depth to about 12. Now this can go all the way up to 99 as well, but we will completely change the character if we make it more than, say, 20. So we'll stick with 12 for now. But you know, you feel free to experiment on your own DX27. How can you possibly learn to program FM voices unless you play around with it and experiment? So we've set our pulse modulation depth to 12. Now we can be sure that we are going to get that to work, or at least I can be sure, because the default for the sensitivity, notice where it says here modulation sensitivity, the default for pitch sensitivity is already set to 6. That's what the preset does. But if you ever turn up your pulse modulation depth, your pitch modulation depth, and you find that you don't get any kind of pitch modulation, then you need to check your pitch modulation sensitivity. So the PMS and the PMD work together to get you pitch or vibrato, whereas the AMD, notice the AMD, which is amplitude modulation depth, and the amplitude modulation sensitivity, AMS, work together. See, the AMS is all zeros. So really and truly, we wouldn't be able to get any amplitude modulation going, which is more like tremolo, which is normally called tremolo, without affecting that. So, but we're not interested right now in that. So we go back and we touch the keyboard having set our pitch modulation depth to 12. And that's a very nice organy type of sound now that we've got on our keyboard. So you can, you know, you can make a whole lot of different mellow and more aggressive organ type sounds by playing with your vibrato depth, as well as by altering your frequency ratios on those 4 operators. Now, just to give you an example before we move on of what would happen if we decided, for example, to change our ratio from one of those. Let's press our frequency ratio button, and let us, for example, change our ratio to a non-integer number like 3.46. To go one step further and turn our lovely organ sound into random noise, which is a spread of all frequencies changing with random amplitude, random frequencies and random amplitude, all we have to do is to take off our vibrato, which we've done now, and then we need to do 2 things. We need to change the ratios to non-integer values. Remember, we had them simply set to 1, 2, 3, and 4. Well, now we're going to push up the lever, and we're going to make the first ratio equal to 25.95. We're going to come and make the next one equal to 0.5. We're going to come and make the next one equal to 5.65. 5.65, and then we're going to come and make operator 4 equal to 0.5. Right. Now if you touch your keyboard at this point, just having taken off the vibrato and changing our organ sound, now we're going to get a very high pitched noisy metallic sound. Okay? Now what do we need to turn that into complete noise? Well, we've got to have equal amplitude on the operators, because the way we have it set up right now, operator 1, which has the 25.95, which gives you that terrible high pitch, is set to maximum. If we modulate that operator more, so that we can set them all to 90, so that we're doing heavy modulation, because remember that these operators are actually modulators, because they're into the stack, higher up the stack. So we go and we set them all to 90, as you can see. Well, it doesn't really matter if it's 90 or 91. But they're all now set to 90. Now what do we get when we touch the keyboard? White noise. And its frequency doesn't change no matter where on the keyboard we touch it. So any key is going to give rushing wind or just white noise like what we get on an analog synthesizer, because we're modulating with equal amplitude at a great range of unrelated frequencies. So the ratios have randomized our frequencies and the levels have randomized our amplitudes. We've increased the amplitude across all frequencies basically. Well, that's it for today. Thanks for watching the Stephen Mendes channel as we teach you how to use your wonderful DX27 digital FM synthesizer. See you in the next video.